Now, can you hear it this time?
Hello, everyone.
Yeah.
My name is Buckley, representing
Perfect.
Technological University Dublin. Today, I will be giving a talk on a trial of a thermophotovoltaic device that was tested in a cement cool-down grate. I'll be presenting a background of the technology, doing an introduction, showing experimental methods, results, and a quick conclusion, and hopefully there will be some time for questions at the end. A thermophotovoltaic or TPV device uses the photoelectric effect to generate electron-hole pairs from thermal radiation. Typically, they will use a selective emitter and may also use a spectral filter. But in this case, we only use 2 gallium antimonide cells. Here are some past examples of TPV systems that were built. As time has gone on, the design philosophy of TPV generators has become more advanced and therefore functional. There is a broad consensus that industry in general wastes 60% of their thermal energy. In the EU, it is estimated that 279 terawatts of heat energy can be reclaimed. Most of this is low-grade heat, which is unsuitable for TPV systems. There have been some niche industrial areas at high temperature that are suitable for TPV, which have been identified. These would also be unsuitable for larger, more cumbersome methods of recovering heat due to the awkward shape and size of these areas. Suitable industrial sectors are places with high-grade waste heat like cement, incinerators, glass, oil, etc., where we want to convert this waste heat into used energy for the entire factory. To recover heat currently, organic Rankine cycle steam turbines have about 30% system efficiency, but are very volumetric and expensive. TEGs work well for low-grade heat, but require one surface to be hot and the other to be cold. Relying on the Seebeck effect, they are about 8% efficient. TPV can operate at high temperatures without the cells being at those temperatures, and are ultimately an optical devices with a system efficiency of about 25%. Our DM demonstration model used 2 gallium antimonide cells orientated away from each other at one end of a heat-resistant probe. They were put in series to increase their voltage for a higher resolution of the analog to digital converter. There is a slight risk of shadowing because they are in series, but this isn't enough power to damage them, and the heat sources used were homogeneous by design. A variable resistor was used to change the load experienced by the cells. This is controlled by a microcontroller. Since we know the resistance of the variable load at any given time, since we know the bit value of the PWM, we can measure the voltage across it, and we can know the current through the shunt at any given time since we know the resistance. The bit value is correlated to the resistance of the circuit as it does a sweep. Different functions were used to get close to matching the data, but this one worked the best with the highest R² score, indicating it was the closest at describing the data. This is the winning model used to correlate the bit value to the resistance of the shunt. The parameters of this model are saved, and the function is later used to convert bit of the microcontroller pulse width modulation to a resistance value. An R² value is recalculated as a check test. The general R² equation is also shown, but I won't elaborate here. We used a lab electric furnace to expose the TPV cells to a desired temperature. We couldn't exceed 900 degrees Celsius as this would cause the glass to become opaque. Multiple 20-minute acquisitions from 900 to 500 degrees C were taken in 50 degrees C increments. We also did a longer 2.5-hour acquisition to see how these parameters drift. First, I'm showing 500 degrees C results to show that this temperature is unsuitable for gadolinium antimonide material. The expected voltage is more like 0.8 volts, but here we see 0.5 volts open circuit. We used the function fit from before to convert the bit value into resistance. This allows us to plot voltage versus load resistance. At 900 degrees C, the cells create a voltage open circuit of 0.8 volts, which starts dropping after bit 60, which is when the pulse width modulation average voltage becomes high enough to start closing the transistor gate. The knee, in this case, begins at around 10 ohms, and it is from here until 0 ohms that most of the data is taken, and the circuit varies the load resistance as a limit of 0. We convert the voltage measured across the variable resistor and the raw bit value of the microcontroller to volts versus resistance using the previous calibration model again. At 500 degrees C, the temperature is unsuitable for TPV for this material as it generates little current. We know the current because we know the voltage and resistance. We can multiply current and voltage to get power, which, as you can see here, the model doesn't pick up very well. At 900 degrees C, the IV curve looks much better since the voltage is now becoming louder than the noise. Power is calculated again from voltage and current, but this method is quick and easy, however it suffers from stacking errors. That was one sweep in a long series of sweeps. At 500 degrees C, the voltage open circuit is 0.58, which is not very high for this material. At this temperature, there's almost no current. The maximum PowerPoint fit function failed due to the low data quality at this temperature. At 900 degrees C, the voltage open circuit is 0.81 volts. Remember, these cells are in series, which is this is more of an expected voltage. Current at this temperature is approximately 1 amp, and the maximum power point of the two cells is 0.375 watts. Here we see the prolonged exposure at 900 degrees C. The voltage remains stable while temperatures are maintained at 900 degrees C. That gap that you see there, that comes from unplugging the data acquisition unit to see if it reports the same values as the multimeter, which it does. The current is driven more by intensity as the furnace warms up. The power drifts upwards slowly as the furnace temperature settles as well. You can see it here on that plateau. The DM was exposed for 2.5 hours at a plateau of 900 degrees. So the 2.5 hours that I'm referring to here is from this point to this point. The demonstration model was used at the hottest part of the cool down grate, which is usually used for thermocouple probes. Other instruments like thermal cameras estimate the temperature at this region to be about 1083 degrees C. Hence, 3 1-minute acquisitions were recorded. This is because the demonstration model had to be allowed to cool down between each sweep. The glass, if it was allowed to reach those high temperatures, would become opaque. The concern was not over the TPV cells themselves. In this cool down grate, the voltage open circuit at about 1080 degrees C was higher than before at 0.86 volts, as expected. The voltage knee occurred below 10 ohms as before. A higher light intensity will lead to a higher current, and this is seen from the cool down grate. from these results, we get a slightly higher result than we got from the 900 degrees C experienced in the electric furnace. The maximum power point measured almost reaches 0.5 watts, and if we look at the 3 acquisitions that were taken, the voltage open circuit drifts lower with progressive sweeps, suggesting a lower apparent temperature seen by the cells, and the current also drifts down with each sweep, which suggests a reduced light intensity, which is probably caused by damage to the glass. Maximum power point remains quite consistent, but this experiment needs to be done again for a longer period of time. The band gap energy of the material corresponds with the Vine's temperature of 1400 degrees C, and so it is expected to see the highest efficiency at that temperature. A power function is used here as light intensity increases with t to the power of 4, but that's the Stefan-Boltzmann equation, but it is suspected that a polynomial would be validated at those higher temperatures due to losses from thermalization at those very high temperatures. Temperatures exceeding 1050 degrees are likely to damage the glass, and the DM produced a maximum power point of 0.16 watts per centimeter squared in the cool down grate. Now I'm going to show quickly how the efficiency was estimated via calculation. First, light falling on the TPV cells was calculated. The furnace temperature is controlled by a microcontroller switching the heat elements on and off. It is assumed that the heat loss through the insulation must be compensated by the heating elements. The elements heated the surrounding material, so the cells on average receive a consistent and homogeneous source of thermal radiation. This static temperature requires constant replenishing of energy to maintain any particular temperature. This common formula to calculate the heat loss through a wall is used where K is thermal conductivity, A is area of the wall, L is thickness, and T1 minus T2 is the difference between the inside and outside temperature. The thermal conductivity for aluminosilicate refractory brick changes depending on the temperature. So a model is used in place of the K value. The energy loss is assumed to be pumped by the heating elements inside the oven, which ultimately radiates from the inside surfaces onto the TPV cells. An average distance to the walls is calculated, and therefore intensity of light falling on the cells can also be calculated. The electrical output of the cells in watts per centimeter squared is divided by the light intensity in watts per centimeter squared, which allows the efficiency to be estimated. A fit of efficiency is made where the mode is postulated to be 1400 degrees C, which is expected because of the bandgap energy of the material, and the rest of the function is optimized by PC. This is a Gaussian function. The light intensity will be measured in future tests, and this prediction will be validated or invalidated. The estimated efficiency is lower than the quantum efficiency at 1200 degrees C. This is by Zenker et al. And higher than the TPV array made by Zafir Utlu 2019, where he used a burner torch as a heat source. So now I'm going to give a brief conclusion to these experiments. It is predicted that a gadolinium antimonide cell based device would generate around 4 kilowatts per meter squared at 1400 degrees C at 50% efficiency before cooling loads. Many aspects and intuitions around design of such a system were learned from the trial, but it's hard to express here. In the cool down grate, the DM generated 1.65 kilowatts per meter squared at the maximum power point. Further work will include a filter and selective absorber emitter our selective absorber emitter, and will validate efficiency calculations as well as perform a long form testing for a reliability characterization. And here are the references used in the accompanying paper. I'm just putting it here as a courtesy. And I would like to thank Enterprise Ireland for funding this work and the support of TU Dublin staff, in particular Neil Brannigan and Brendan Kennedy, for the use of their electric furnace, James Weir and the Irish Cement staff, as well as my co-authors Iftikhar Hussain and Brian Norton, and last but not least MITAB for the opportunity to present this work. I'm happy to take any questions.
Okay.
Okay. Hi, Graham. Thanks for a nice presentation. I just before answering questions, can you give the host to me in the Zoom?
Yep.
Okay, thanks. Okay, great. So for our audience, for our participants, does anyone have a question for Graham? So Graham, for your sorry, I'm not an expert for this field, but just wonder, like, it seems like a thermophotovoltaic device is just convert heat to electricity power. I'm just wondering, curious about the temperature range. I see the range can go very high temperature, about like 600. What about like low temperature? Like, is there kind of a temperature limitation?
So there's different materials that are used that could be used for thermal photovoltaics. The reason here I mentioned gallium antimonide is because it has the highest efficiency. There are other materials such as indium gadolinium arsenide that can be used at lower temperatures.
Okay.
The temperature that's useful for the cell's material depends on the band gap energy.
Okay, good.
When you reduce the band gap energy to very low temperatures, let's say 400 degrees C, the reason it's not a good idea is because the band gap energy is so low that electron hole pairs can recombine through Brownian motion. So that's why at these temperatures, the efficiency is much, much worse. So it's not worth it.
Okay, so yeah, I got what it means. Basically, for your device, for higher temperature, the efficiency can be higher, if I understand correctly.
Yes, correct.
Yeah, okay, cool. Thanks for clarifying. Okay, does anybody have other comments or questions?